Hello and welcome to Matlab programming for numerical computations. We are in module number 4 and this is the last lecture of this module. In module 4 we have been covering linear equations of the type Ax equal to b, where A is an n by n square matrix and b is an n by 1 column vector. In this lecture, we are going to cover a special type of algorithm known as the Thomas algorithm or tridiagonal matrix algorithm. So let us look at how a tridiagonal structure looks like. The matrix A shown over here is what a tridiagonal matrix will look like. So basically there's diagonal elements d1, d2 up to dn. Okay, there is one subdiagonal row which is L2, L3 up to Ln, and one super diagonal, that is one above the diagonal, which is U1, U2 up to Un minus 1. Okay, this is known as a tridiagonal structure. Lot of engineering problems end up reducing to a tridiagonal matrix structure, or sometimes what we have is what is known as banded diagonal structure. Tridiagonal is a specific example of banded diagonal structure with the bandwidth equal to 3. So let us look at one particular example where we get a tridiagonal structure. This example is from the Computational Techniques course, Module 3, Part 5, and the link for which is given over here. Okay, if we have a rod through which conduction is taking place, one end of the rod is held at 100 degrees Celsius and the other end of the rod is at 25 degrees Celsius, and this rod is losing heat to the surroundings. Then the overall model for this system can be derived to obtain something like this. Okay, now if we want to solve this set of equations, we can use the numerical differentiation that we covered in module 3. Okay, and the central difference formula will be of this type. Now this you substitute it to the left hand side, and right hand side becomes gamma multiplied by Ti minus 25. You write this for multiple locations, that means at the initial point T1, the next point T2, T3 and so on up to Tn plus 1. Okay, if you do that, you will end up reducing this particular differential equation into n linear equations in n unknowns. And these linear equations, for example, the example that we covered in a computational techniques lecture, consisted of discretizing in 10 intervals. If gamma equal to 4, then the first equation is gonna be T1 equal to 100. And for all the nodes within the rod, we get equations. If we do the derivation, we'll get the equations of the type T1 minus 2 plus alpha T2 plus T3 equal to beta, and so on and so forth. Okay, so what you can see over here, the first equation, the diagonal element is 1 and the non-diagonal elements are all 0, and for the vector b, the first element is 100. If you look at the next equation, the diagonal element is minus 2 plus alpha. Okay, and the subdiagonal and the superdiagonal elements are both equal to 1. So let's go on to Matlab and start trying to solve this particular problem. My Tdma. I have already created a skeleton of the structure. So first step that we are going to do is we are going to create the problem matrices. Okay, if we go and look at PowerPoint again, okay, what we are going to have is basically the A matrix of this sort. We have the diagonal elements which we are going to store in vector D, the super diagonal elements where we are going to store in vector U, and the subdiagonal elements which we are going to store in vector L. That is what we are going to do. Okay, so our vector L, L11 is going to be equal to 0. Okay, let's look at this again. L11 equal to 0 because there's no element in the first row for L, and in the last row Ln is also equal to 0, so we will do that as well. Okay, Ln, so we should actually, let's just put this as Ln plus 1, n equal to 10 because 10 intervals, and therefore we have 11 nodes. So this is also equal to 0. We need to create n first. In this case, our n was equal to 10, our alpha was equal to 0.04, and our beta was equal to -1. Let's just check those things. Alpha equal to 0.04, beta equal to -1. Yeah, and n equal to 10. Okay. Likewise, for u also, we are going to get u 1 comma 1 equal to 0. Remember, the first equation was just t1 equal to 100. So u1 comma 1 was 0 and un plus 1 comma 1 was also equal to 0. Again, recall the last equation was also t11 equal to 0. Sorry, t11 equal to 25, which meant that the non-diagonal elements were all 0. And the entire set of diagonal elements that we have seen is the first guy and the last guy are both equal to 1, whereas everything else is minus 2 plus alpha. Okay, so we will write d 1 comma 1 equal to 1 and d n plus 1 comma 1 equal to 1 again. And likewise, b 1 comma 1 was equal to 1 and was equal to 100, and b 1 n plus 1 comma 1 was equal to 25. So that's the structure that we have created. The first and last rows are taken care of. Now we want to take care of all the middle rows. So L2 to n comma 1 equal to, we will decide this, u2 to n comma 1. Again, we need to decide this. I'll just put question marks here. Again, this is an error, but we will change that immediately. 2 to n comma 1 equal to question marks, and our b 2 to n comma 1 again equal to question marks. So let's see what we need to put in our vector L. Okay, so our vector L, as we had said, was 1 multiplied by t1, that gets L, and 1 multiplied by t3, that is in u. So L3 is gonna be, or sorry, L2 is gonna be equal to 1. L3 is going to be also equal to 1, U2 equal to 1, U3 equal to 1, and so on. So all the middle elements of both L and U matrices are all equal to 1. So we will put this. The diagonal elements, if we check, the diagonal elements are minus 2 plus alpha. So we will put that minus 2 plus alpha, and our B elements are equal to beta. Yeah, so we'll put that beta. And with this, we have done with creating the problem matrices. We've saved this. Let's go to Matlab and run my Tdma to ensure that we do not have errors at this stage. Okay, we do, right? So let's say where, okay. So here, if you look at this particular code, what I have done is I have made a typo. Instead of putting a comma over here, I have put a dot, which is a typo. So let me go and change that and save, and let me run it and see whether we get errors. So it doesn't look like, yeah. So CLC. What I had also done was create a small function called show matrix. So if I call this show matrix and give LDU, okay, I'll get our A matrix over here. Okay, this is just so for our ease of discussion, and I will just print first 5 elements of this. Okay, so these are the 5 elements, and this looks exactly as we wanted. Our first guy is gonna be 1, our second guy is 1 minus 2 plus alpha and 1, the third guy is 0, 1 minus 2 plus alpha 1, so on and so forth. Okay, and if we were to print out the entire A matrix, we will get the desired result as well. Okay, and let's also print out the B vector. And yeah, so this is the B vector and this is the A matrix. Okay, now at this stage, what we can also do is solve it using the methods that we have seen in lecture 4.1, which means our x, we'll call this as x1 equal to A backslash B, and this is the solution. Okay, so this is the overall temperatures in the rod going from one end to the other, from the 100 degrees Celsius end to the 25 degrees Celsius end. And this is the result. What we want to do is reproduce this result not using the slash, but using the Tdma algorithm. Yeah. So how does the Tdma algorithm work? You can go again to this link that is shown over here, and you can see this video to try to understand how the Tdma or the Thomas algorithm works. We are gonna just use that. It's kind of similar to the Gauss elimination, except we account for the fact that all the other elements except D, L, and U are zeros. So we do not need to do all the computation that Gauss elimination does. That's one. The second difference is that in each step we are going to divide by the pivot element D1, A11, A1, A22, so on and so forth before doing a typical Gauss elimination step. So let's go and start working that out. In the Thomas algorithm, the first step is going to be normalize by dividing. Okay, let us put this in a loop for I equal to 1 to n plus 1. The loop should not be n plus 1. We'll come to that later. But for now, let's just try to do it for the entire loop. Okay, so the first row is going to be divided by di, or any row is going to be divided by d. So at whenever ai is the pivot element, everything to the left of the pivot element is already 0. So we don't have to worry about dividing anything in the L vector. We only have to look at the D vector, the U vector, and the B vector. But keep in mind that because we are dividing by D itself, we don't have to do anything with respect to D vector either. So what we are going to do is ui is going to be nothing but ui divided by di, and same thing with b also. Bi equal to bi divided by di, and di is gonna be equal to 1. Why? Because the di is going to be old di divided by itself, so therefore it's equal to 1, and that's the only thing that we need to do. Let's also put end over here. Okay, so we ended up normalizing it by dividing with di. So that's the step that we are going to take. So that's the first step with respect to normalizing. So what we did now was with a11 as the pivot element, row 1 was divided by that pivot element. So that in the first row now we have 1 u divided by d, 0, 0, 0, and so on, and the last guy is b divided by d. Okay, now we are going to use that pivot element to make zeros in the first column. Now, where do we need to make 0? We only need to make 0 in the row number 2 or row number I plus 1. Why? Because that's the only non-zero element. So Li plus 1 is the only non-zero element in that pivot column, using pivot element for elimination. Okay, so our alpha is going to be nothing but Li plus 1. Why? Because our di, that means aii, is already equal to 1 because of this step. Okay, so if we want to make 0 in the I plus 1th row, ith column, then we need to just multiply row I with Li plus 1 and subtract it from row I plus 1. And that is essentially what we are going to do. Your alpha is just going to be Li plus 1 divided by di, but di is already 1, so you don't need to make that division. Okay, so alpha equal to Li plus 1. Li plus 1 is going to be equal to Li plus 1 minus alpha, okay, which is basically going to be equal to 0. So why should we do this extra calculation? We don't need to do this extra calculation. We can directly put that equal to 0. And that is essentially what we have done. Okay, now the di plus 1 is also going to change. And the di plus 1 is going to change because di plus 1 is going to be di plus 1 minus alpha multiplied by ui. Minus alpha multiplied by ui. Okay, and the same thing with b also. Bi plus 1 is gonna be equal to bi plus 1. Okay, what is above bi plus 1? Above bi plus 1 is exactly bi. So it's gonna be minus alpha multiplied by bi. Okay, so that's the thing. Now what about ui plus 1? The element above ui plus 1 is 0. The element above this guy is 0. So if we do any kind of a computation, it is still gonna result in ui plus 1. So we don't need to change ui plus 1. So we are done over here. So that's all we need to do with respect to Gauss elimination. Okay, this Gauss elimination is applied to a special structure, the banded structure of the tridiagonal matrix. So let's now run this. Okay, I expect an error, and I'll come to that when we actually get an error. I expect an error, and I will explain that in a minute. Let me just run it. Okay, and let's see what error we get. Okay, error is the attempt to access L12 index out of bounds. So what is happening over here is this, is when I is equal to n plus 1, which means when I equal to 11, okay, we have done this normalization, that is fine. However, this cannot continue. Why? Because there's nothing called L12 or D12 or B12. Our matrix ends at row number 11, column number 11. Okay, so what we needed to do really was we need to do only 10 row operations and not 11th row operation, because R11 is not going to be used to change anything below, because R11 is the last row. So we need to use this to go from I equal to 1 to n only. Okay, so let's do that. Let's go to Matlab, you clear all CLC and run my Tdma. Okay, and we have our results over here. Okay, now what we want to do is we want to check our A matrix. So A is show matrix, and then we want to display A 1 to 5, 1 to 5, and see how they look like. Okay, so this is how our A matrix is gonna look. So the A matrix has now an upper triangular structure and a special kind of upper triangular structure. Only the U elements in the upper triangular structure are non-zero. Everything else is zero. So we have your AII as non-zero, AI I plus 1 is non-zero, and AI I plus 1 is nothing but equal to UI. Okay, so when we do back substitution, okay, AII is already equal to 1. When we take this guy to the right hand side, we are gonna get BI minus UI multiplied by XI plus 1. Okay, and that is our XI. We don't need to divide by A11 because A11 is already equal to 1. So our back substitution is also significantly simplified. Okay, so our first guy is first step is going to be, we are going to say x equal to zeros n plus 1 comma 1 and x n plus 1 comma 1 is gonna be equal to b n plus 1 divided by d n plus 1. Okay, why do we need to divide by d n plus 1? Is because all these things we have done it only until row number 10. Row number 11 we have not yet divided by the pivot element, so we need to do that in the back substitution step. Okay, and then we have the for loop for back substitution for I equal to n in steps of minus 1 to 1. Okay, and our xi we said was gonna be equal to bi minus ui multiplied by xi plus 1. Keep in mind ui is nothing but ai comma I plus 1. Ai comma I plus 1 is multiplying with xi plus 1. We take that to the right hand side, subtract it from bi and divide by 1. We don't need to do that division because dividing by 1 is going to lead us to the same result, and end. Okay, and that is the back substitution that we needed. So let's see whether we are going to get any errors or this is going to run like a charm. So let's me click the run and let's go back to our command prompt and see what solution x we are getting. Okay, so this is what we are getting as x. Let us check back with x1 and compare the two results. Okay, so as we can see, the results using the Gauss elimination that Matlab used when it did backslash and the results using our Tdma algorithm, they are matching exactly. Okay, so Tdma algorithm is nothing different. It does nothing different from Gauss elimination with back substitution, except for the fact that it exploits the structure of the tridiagonal matrix. That means there are only three elements in any row which are non-zero, and therefore we need to take significantly lesser number of computations compared to a standard Gauss elimination algorithm. Okay, so that's what I wanted to cover with respect to Thomas algorithm. What I would put as an exercise for you guys is to do the same problem but with a larger number of examples, and that is going to be first problem. And the second problem, what it is going to be is to solve the exact same problem that we have done in this lecture, to solve this exact same problem but using the Gauss elimination method. So here you will need to construct your A matrix and your B vector and compute this using Gauss elimination. So what you need to do is basically you create this A matrix and the B matrix. I have not shown you my code, which is the show matrix code, which I've used in order to calculate the A matrix from L, D and U. That is the main crux of your second problem of this assignment. So with that, I come to the end of lecture 4.5 and indeed to the end of module 4. In module 4, we have covered solving linear equations of the type Ax equal to b. In lecture 4.2, we covered naive Gauss elimination. In lecture 4.3, we changed the Gauss elimination to Gauss elimination with partial pivoting, as well as we saw very quickly how the LU decomposition works. In lecture 4.4, we moved on to what are known as iterative methods and covered Gauss-Seidel method. And in today's lecture, that is the final lecture, we covered a special method known as Thomas algorithm for solving tridiagonal system of equations. Thank you, and I will see you next week where we are going to start working on solving nonlinear equations. Thank you and see you in the next week.